So, good morning, dear friends. Today we have discussed the second method, that is the cantilever method, which is used to find out the bending moment and shear force in the multi-story building frame. So, as we know that in building frame, actually, when we can find out the degree of static redundancy, DSI, that is equal to number of reaction component minus equation available plus 3 times the area of the closed loops. When number of stories are more, then redundancy increases, and that's why it is better to use some approximate methods. There are basically three methods for the horizontal load, that is the wind load, or we can say that the seismic load, and second is uh, the method which is used for the vertical load, that is the live load and the dead load and their combination. So the uh, three methods used in the horizontal load, that is called as the lateral load, are portal frame method, then cantilever method, and the factor method. And for the vertical load, we have used the substitute frame method. Only one method is there. So of course, there are certain assumptions when we use the approximate methods. As we know that in portal method, there are two assumptions. First is the point of contact flexure occur at the mid height of the column and mid span of the beam. Here also in cantilever method, we have used the same assumption. That means the first assumption is same. There is no change. But in the second assumption, the direct stresses, that is the axial stresses in the column due to horizontal forces are directly proportional to their distance from the centroidal vertical axis of the frame. This is the second assumption. In portal method, we have considered the horizontal shear taken by the interior column is double than the horizontal shear taken by the exterior column. This is the assumption. So this is the basically change between the portal method and the cantilever method. So portal method is generally more suitable if the width is more and height is less. That means the low-rise building, and cantilever method is more suitable for the high-rise building. Okay, so let us have the example how to analyze the building frame for the using the instead of portal method we have used the cantilever method. Same problem. So here the load given at the J, that is the top story joint, 90 kilonewton, middle 60 kilonewton, and the bottom 40 kilonewton. Floor to floor height is 3.8 meter. First span is 8 meter and second span is 4 meter. So just we have analyzed. So first of all, we can locate the CG of the frame as per the, we can say that the assumption. So we have considered the centroidal axis. We have considered this is the centroidal axis, vertical red line, and this distance from the, say we can say that the left corner, that left column, that is the ADGJ. From this we have find out the X bar. Okay, so taking moment about the left column, that is the A, D, G and J, and we get the we can say that the CG of the frame. So we have considered here there is we can say that the area of all the columns are same. It is not mentioned in the problem. That's why we have assumed that the area of all columns have or same cross sectional area. Therefore, first column multiplied by area is A and multiplied by distance is 0. So A multiplied by 0. Second column, this is the second column, that is the BEHK multiplied by this distance, that is 8 meter. And third column, that is the CFIJ, and from the this left column A, it is 12 meters. So A multiplied by 12, A multiplied by 8, and A multiplied by 0. That is the moment about this line. Just we can say that we have applied the variance theorems. So is equal to the area of all three columns. So A plus A multiplied by CG of the, we can say that the resultant CG of the frame. So multiplied by x bar. So from this we get the x bar is equal to 6.67. So this is the line which indicate the CG of the frame. So we have considered below this, or we can say that the left side of this section, it is in compression and right side in tension. So the direction of the axial force can be changed. So this is the figure. So here it is observed that this is the x, we can say that the x bar is equal to 6.67. So this is x1, that is from the leftward side column. So we have considered, as per the first assumption, the point of contraflexure always lie at the center of the column and center of the beam. That's why we have considered the section 1 1. This is the say node 1, node 2 and node 3, where we have considered exactly at the center or point of contraflexure. So h by 2 is equal to 3.8 divided by 2, it is 1.9 meter. So here we have considered this is the assumed direction. V1 is upward, say V1, V2 is downward, and V3 is again downward, because this is on the right side of the section and this is the left side of the section. If we have considered upward, this will be downward. Okay. So as per the second assumption, what is second assumption? Second assumption is the direct traces, that is the axial traces. Here we have shown the v1, v2, v3 like that in the column due to the horizontal forces are directly proportional to their distance from the centroidal axis of the axis from the area. Okay, so we can say that the trace is equal to force divided by area. So axial force we have considered v1 for the column number 1 divided by area a1. So v1 by a1 is the trace for the column number 1, axial trace for the column number 1. v2 by a2, it is related with the axial trace for column number 2, and v3 and a3, it is related with the column number 3. Okay, and we know that the cross-sectional area of the all column we have assumed same, and that's why a1 is equal to a2 is equal to a2 is equal to a3 is equal to a. So this will be vanished, and we get the trace divided by centroidal distance for the this distance from the column number 1 or from the node number 1 to the CG, it is 6.67. So the V1 by X1 is equal to V2 by X2 is equal to V3 by X3. So therefore, the V2 means this V2 multiplied by V2 divided by X2. So X2 is equal to total distance is 8 meter minus 6.67. So it is 1.33. And V3 means the this total distance. So V3 is equal to 5.33, because this distance is 4 meter and this is 1.33. So it is 5.33. And from this we have find out the relation. So V1 divided by 6.67 is equal to V2 divided by 1.33 is equal to V3 divided by 5.33. So we have convert this V2 and V3 in terms of V1. So V2 is equal to 0.20 times V1 and V3 is equal to 0.8 times V1. Now taking moment about point node 1. So we have taken the moment at this point. So can I say 90 multiplied by perpendicular distance 1.9, it rotates in clockwise direction. That's why we have considered positive. Plus V2. So this is the V2 multiplied by this total distance, that is 8 meter. Again, this will be rotated in the same direction. So positive. Then V3 multiplied by total distance is 8 plus 4, that is 12 meter, is equal to 0. And from this, again, we have eliminate V2 and V3 by V1. V2 is equal to 0.20 V1 and V3 is equal to 0.80 V1. And that's why we get V1 is equal to minus 15.18 kilonewton. Minus sign indicate the direction of this axial force is downward direction. So this will be in downward direction, this will be in upward direction, and this also in upward direction. So V1 is equal to minus 15.18. Put the value here. V2 is equal to, we get the minus 3.03. That means we can change the direction, and V3 is also equal to minus 12.14. Again, we can change the direction of the V1, V2, and V3. Okay. In this way, we can find out the axial force in the column 1, column 2, and column 3 at the top story. Similarly, we have considered the section 2, that means the intermediate story. We have considered the point of contraflexure at 6, 7, and 8. We have given the number to the point of contraflexure for the intermediate story. So this is 6, 7, 8. So again, X bar is same. V7, here we have considered the V6, V7 and V8 for the node number 6, 7 and 8. So again the proportion of V6, V7 and V8 is similar to the previous one. That means we get the similar to V2. Here we have considered the V7, V7 and V8 like that. So we get the 0.20 times V6 and V8 is equal to 0.8 times V6. So again taking moment over the 0.6 and repeat the same procedure. So 90 multiplied by 3.8 plus 1.9, it is 5.7, and 60 multiplied by 1.9 in the same direction, clockwise direction. Then V6 is 0 as it's passing from the node 6, but V7 multiplied by this 8 and V8 multiplied by 12 in the opposite direction. So we get the answer. Again we have eliminate this V7 and V8 by V6 and we get the value of V6 is equal to 55.98 kilonewton, V7 is equal to 11.20 kilonewton, and V8 is equal to 44.78 kilonewton. This is the second. Third one, then we have considered the third section. At the point of contact flexure, node number 11, 12 and 13. That is, we can say that the at the bottom story. And again repeat the same procedure. Again V11, V12 and V13 have the same proportion as the first one. So V12 is equal to 0.2 times the V11 and V13 is equal to 0.8 times the V11. Okay, again we have taken the moment about the node number 11 and repeat the same procedure. So 19 multiplied by this total distance, that is 9.5, 60 multiplied by 5.7 and 40 multiplied by 1.9 in the same direction. Then V12 multiplied by 8 and minus and minus V13 multiplied by 12 is equal to 0. Again eliminate this V12 and V13 by V11 and we get the value of we get the value of V 11, 12 and 13. Okay, so in this way we have considered the three section, one section, two section and three section, and we get the axial force, that is the V1, V2, V3 like that, 6, 7, 8 and 11, 12 and 13. Okay, similarly now once we find out the axial force, we can easily find out the moment and the shear force in the we can say that the beam. So this is the figure where we have considered when we cut the frame at the point of contact flexure. This is the point of contact flexure for beam, that is H4 and V4. Here H5 and V5, H9 and V9, here H10 and V10, equal and opposite. When we cut the frame at the point of contact flexure, there is no moment is 0, but only shear force and the axial force is there. So H9 is there, and similarly we have considered the every one part. So we get the value of H1, H4, like V4 and the moment also. Okay, when we can find out the moment, for example for the joint J, here this J is connected with the J2K beam and J2G column. Here when we take the moment for the column, can I say H1 multiplied by 1.9, that gives the moment at J or J2G, and similarly this force in the opposite direction to this for the when we consider the this portion, and again we get the same answer, that is the H1 multiplied by 1.9, that is H by 2 in the same direction, because the point of contact flexure always lie at the center of the column. So when we consider the joint J, we know the moment at J for the column. So what is the moment at J to K? When we take summation of moment of all the moment about the J is equal to 0, we get the same answer but in the opposite direction. So moment is clockwise at J to K, that is equal to moment in the column J to G. In this fashion we can find out the moment in the other column as well as other beams. Here we know that this there is when we join this only moment is there, that's why this moment and this moment is same. And when we consider the joint J, we know that the moment in the column K to H, and when we take the summation of moment at point K is equal to 0, this moment is known because this moment J to K is equal to K to J. This moment is known, this moment is column moment is known, so summation of these three moment is equal to 0. That's why we can find out the moment in the column K to L, or we have considered the joint L. We can find out the moment in the L to K is equal to moment in the column L to I, and in this way we can find out the column moment as well as beam moment. So this is the cantilever method. So in this way we can find out the, that means we have considered the free body diagram for the cut the frame at point of contraflexure. At every point of contraflexure in the beam and column, consider free body diagram taking moment, and we can find out the H1, H4. V1 is known to you. We can find out the V4. That means summation fx is equal to 0, summation fy is equal to 0, and moment about the any point or joint J is equal to 0. We get the moment in the column or moment in the beam. Okay, in this way we can find out the column moment and the beam moment, and this is the generally diagram. I have not mentioned here the numbers, but it is observed that for the beam, the direction of the moment is like this: one is downward, other is upward, because the point of contraflexure is always at the center. That's why this moment and this moment is same, this moment and this moment is same. Similarly, for the column also, this moment and this moment is same, and it cross at the center, because the moment at the center, that is the point of contraflexure, it is 0. So this is the bending moment diagram for the column and for the beam. So in this way we can find out the we can say that the bending moment, shear force, axial force in the column and the in the beam. This is the another problem by somewhat slightly different method. Method is same, concept is same, but we have considered instead of finding the h1, h2, h3, we can find out the we can say that the moment. So let us have just look this problem. This is the 3-bay, 2-story, first and second. 30 kilonewton load is applied at the I node, and at E it is 60 kilonewton. Floor to floor height is 3 meter. And for the span of the beam, I to J 3.5 meter, J to K 3.5 meter, and K to L it is 3.5 meter. And as the frame is symmetrical, definitely we can say that the CG of the section at the center. So let us have the problem. This is the problem. So point of contraflexure always lie at the center. So here consider the at every node or at every center of the beam and column we have given some number for our convenience. So 1, 2, 3 indicate the center of the beam, and 4, 5, 6, 7 indicate the center of the column. Similarly for the EFGH 8, 9, 10, and for E to A 11, F to B 12, G to C 13, and H to D 14. In this way we have given the numbering, that is the node. As per the assumption, again we have considered the axial trace. Here the cross sectional area of the column is same. That's why trace is equal to trace for the column number 1. Axial trace is V1 by A. For the column number 2, V2 by A, V3 by A, V4 by A. So A will be vanished. We get the V1 by X1 is equal to V2 by X2 is equal to V3 by X3 is equal to V4 by X4. And we have get the relation between the V2, V3, V4 in terms of V1. Okay, so H4, H5, H6, H7, these are the horizontal forces. V4, V5, and this is the CG, center of the section. As the frame is symmetrical, that's why this is exactly same, 5.25, 5.25. So on the left side of the section, the direction of the V4, V5 is downward, and right side it is upward, because we have considered the in this direction the frame may be in compression, and in the second side of the section it is a tension, like that. Okay, so in this way we can find out the so here we have, instead of considering the node, here we have what we have considered: H4, H5, H6, H7, that is the horizontal force in the column is equal to, we can say that the summation of fx is equal to 0. We get the h4, 5, h6, h7 is equal to 30 kilonewton. So taking moment of the point P, that means the about the CG of the section, and therefore we get the V4 multiplied by 5. This is the V4 multiplied by this distance, that is 5.25. V5 multiplied by this distance, that is 1.75. V6 multiplied by this distance, the direction of the all the moment is same, that is the clockwise. That's why V6 multiplied by 1.75 and V7 multiplied by 5.75 is equal to, we have considered the H4 multiplied by this distance, that is 1.5, H5 multiplied by same distance, H6 multiplied by same distance, and H7 multiplied by same distance. So 1.5 is common, and H4, H5, H6, H7 is equal to 30. We have put here, and we have convert this V4 in terms of V5, V6 in terms of V5, and V7 in terms of V5. And using same put here, and we can find out the V4, V5, V6, V7 like that. Okay. This is the second method, or slightly different, but you can, when we have considered the moment at this point, so no need to convert this, consider all these things. We are directly getting the answer. So it is up to you, either use the previous method or this method. So again, we have considered the point of contact flexure for the beam and the column, that is for the top story, this one, and apply the summation fx is equal to 0, summation fy is equal to 0, and moment about the point I is equal to 0. We get the h1, h1, h4, h5 like that. Okay, this is the method. That means we have used simply the concept of the equilibrium, and we get the H6, H7 like that, all four. And then again we have considered the second story, repeat the same procedure. The proportion as the trace is same, axial trace is same, that's why the proportion is also same. In the same manner, V11 is equal to 3 times of V12, V13 is equal to V12, V14 is equal to 3 times of V12, because the frame is symmetrical. So again, we get the axial forces and the shear forces, and this is the bending moment diagram. Moment is equal to, we can say that the horizontal force multiplied by h by 2, that gives the moment in the every column. So it is very simple. And for the beam, we have considered the summation of moment at join. We get the moment in the beam. Once we find out the moment in this beam, same moment will be developed in the other end in the beam. 6.74, 6.74, 8.97, 8.97, like that. And this is the bending moment diagram for the column as well as for the beam. So thank you. Thank you very much. So in this way, you can find out the moment and shear force and as well as axial force in the frame. Thank you. Thank you.